Hi everyone. We've been looking at two groups of inverse properties for trig functions and their inverses. In many situations, trig functions and their corresponding inverse functions undo each other. For example, sine of inverse sine, or arcsine of x, equals x if x, this inner argument, is in the range of the outside function, in this case sine. The range is this closed interval from -1 to 1. Under these circumstances, if x is the input, then x is the final output. We simplify this expression as just x under these circumstances. But what if instead of inverse sine, we had another inverse trig function, like inverse cosine or inverse tangent? Then we wouldn't have an inverse property. In order to simplify the expression, we may have to use right triangles. We're now going to use a right triangle method to rewrite an expression like this as an equivalent algebraic expression in x, something that we might have seen in chapters 0, 1, or 2. Think of the quadratic formula. So cotangent and inverse cosine will not undo each other. If the argument were a cosine value, like 1 for example, then you could just work this out. But what if the argument is variable, like x over 3? Then the right triangle method can be used to simplify this more generally. All right, we're going to use substitution. Remember that the output for an inverse trig function can often be thought of as an angle. Let's call it theta. We're going to let theta be the inverse cosine of x over 3, the entire argument for cotangent here. Again, we relate the outputs of inverse trig functions to angles, often. So we want to simplify cotangent of theta. Cotangent of theta, where theta is this inverse trig expression over here. Now, if theta is inverse cosine of x over 3, what can we say as a result? Well, we can say that the cosine of theta is x over 3. Let's write it like this. So we're going to rewrite this as inverse cosine of x over 3 equals theta. I'm using theta because we can think of this as an angle. If you want to use u, for example, that's fine. Well, if inverse cosine of x over 3 is theta, then as a consequence, cosine of theta has to be x over 3. How do you invert this statement? If inverse cosine of x over 3 is theta, then cosine of theta has to be x over 3. It's like a zigzag. Cosine of theta has to be x over 3. By the way, we're going to assume that x will not cause any domain problems. So x, for example, could not be a number greater than 3. All right, cosine of theta equals x over 3. Now, we can use SOHCAHTOA and develop a right triangle model. SOHCAHTOA. We're going to set up a right triangle model so that cosine of theta is x over 3. Let's make this angle measure theta. SOHCAHTOA, ka. Cosine is adjacent over hypotenuse. And you can see that if you set up this right triangle model, then it's true that cosine of theta will be x over 3. Cosine of theta is adjacent over hypotenuse. And then, since we want to find the cotangent of this angle, remember, we want to simplify cotangent of theta over here, then it would help to find an expression for b, the length of this leg here in terms of x. I'm calling it b here. You could call it a or something else. It turns out to be the square root of 9 minus x squared. And how do we get that? Well, what theorem will relate these three expressions for the sides of this right triangle? The Pythagorean Theorem. X squared plus b squared equals 3 squared. X squared plus b squared equals 9. Again, people might be tempted to isolate x squared or b squared on one side because they feel like it, but no, it's not that easy. X squared plus b squared equals 9. And we ultimately want to solve for b, which is buried in there. Sorry, but you're going to have to do some algebra. X squared plus b squared equals 9. First, let's isolate the b squared term. We accomplish that by subtracting x squared from both sides. On the left side, when you subtract x squared, you're left with b squared. On the right side, 9 minus x squared results on the right side. We're subtracting x squared from both sides. Now from the square root method, b can be plus or minus the square root of 9 minus x squared. And then, when applying this method, it turns out that we can delete the plus minus symbol. You can analyze various cases to see why that's true. Here, we assume that theta was acute for our right triangle model, but it turns out that our right triangle model will work even if theta is not acute. We take b equals the non-negative root of 9 minus x squared. And we can label the side like so. Remember, to find cotangent of theta, it's going to be helpful to find an expression for this side length in terms of x. Again, what do we want? Cotangent of this angle theta. Now, it might be helpful to consider its reciprocal function first. What is tangent of theta? Tangent of theta, toa, in SOHCAHTOA, tangent of theta is opposite over adjacent. Tangent of theta is b over x, or the square root of 9 minus x squared over x. That's tangent of theta. But then, to get cotangent of theta, we have to take the reciprocal. Cotangent of theta is then x over the square root of 9 minus x squared. Cotangent of theta is x over the square root of 9 minus x squared. And we're done there. This is an algebraic expression in x. It's something we might have seen in chapters 0, 1, or 2. Think of the quadratic formula. We're allowed to have things like exponents, nice roots, things like that. Now here, a lot of students would try to rationalize the denominator. Actually, I don't recommend that. Generally speaking, this expression here would be considered simplified. If the radicand down here is variable, we actually tend not to try to rationalize the denominator. For example, if x is a messed up number, like the 5th root of 2 or something like that, then we would not be able to rationalize it easily anyway. Not easily. What if x is something like 1 over e? It's basically impossible. All right, so this is our simplified algebraic expression. By the way, the square root of 9 minus x squared is not 3 minus x. We do not take square roots term by term, so please do not try to simplify this to 3 minus x. Now, I claim that this is our expression for cotangent of theta. It's a simplified algebraic version of cotangent of theta, where theta was all this inside here. So my claim is that this expression I have in blue here is equivalent to x over the square root of 9 minus x squared, as long as we don't have any domain problems. Well, let's verify this on Desmos. The original expression is here. Let's graph y equals cotangent of arc cosine or inverse cosine of x over 3. I'll turn that graph on, and it's this red graph over here. It turns out to have VAs, vertical asymptotes, at x equals -3 and x equals +3. That makes sense because if you look here, we know that we're going to be in trouble if x is something like 4, 5, or 6, then x over 3 would not be a cosine value. Likewise, if x were like -4, -5, or -6. Even if x is 3, for example, then we'd get inverse cosine of 1. Inverse cosine of 1 is 0, and it turns out cotangent of 0 is undefined. That corresponds to the VA at x equals 3. Likewise, at x equals -3, we also have a VA. It turns out that the domain for this expression, this function, is going to be the open interval from -3 to +3. Well, guess what? Look at this expression that we're claiming is equivalent to the given expression here. X over the square root of 9 minus x squared. Using the methods from chapter 2, section 2.7, the domain for this expression or function is, again, the open interval from -3 to 3. Notice that at x equals +3 or -3, we're going to end up with a 0 denominator. That corresponds to the VAs at x equals -3 and x equals +3. Again, my overall claim is that this expression, this algebraic expression, is equivalent to the given trig and inverse trig expression. Let's turn on the corresponding graph and see if this red graph just recolors. Yes, it does. The purple graph is the same as the red graph. You can see this flashing, which means that these equations are equivalent and these expressions on the right sides are equivalent. This is not a proof, but it's a very convincing and gratifying check. The fact that these two graphs are the same. Now, I'm not just playing with you. You're actually going to have to work out and simplify expressions like these in your Calc 2 class, Math 151. Because in Math 151, there's a technique called integration using trigonometric substitutions, where you actually have an integral problem and you want to use a trig sub like cosine of theta equals x over 3. And at some point, you have to unravel an expression like this and rewrite it algebraically. You actually do that in a Calc 2 class. So you will see this later on in your calculus adventures. Next up, we're going to talk about how to use inverse trig functions to solve equations. Next time.